Okay. Hi, everyone. Yeah, I'm William Moses, and today I'm going to be talking to you guys about Polygeist, a C and C++ front-end, among many other exciting things for MLIR. Now, this is not just the work of myself, but a large team across various universities, across national labs, and beyond. So, to begin, let's talk about how C and C++ code is compiled right now. So I've got this little C code on the left set, which takes an array, sets every even index to be the same value. First, it goes through the Clang frontend, which parses it and converts it into what's known as an abstract syntax tree, which is shown there on the bottom left, which this is successful in being able to represent the high-level syntactic information, but not necessarily the level at which you'd want to do optimization. The next stage in this pipeline is to lower this to the LLVM representation, which, as we see on the right, is very nice for having some things like static single assignment form and otherwise the level at which optimizations are being applied. But we can also sort of notice that we've now lost a lot of that high-level syntactic structure. Like we can see the fact that there's a loop from that phi node and the branch that goes back to itself, but it's a little bit unclear immediately where that structure derived from. Nevertheless, we can apply nice optimizations on top of it before we eventually create the executable that goes and runs. Now, as I mentioned before, LLVM is great in the sense that it's general enough to represent any arbitrary program, but it has to represent all of that information inside of a single low-level IR. So immediately, this causes us to lose that high-level information, such as control flow constructs like if, for, and while. Any other higher-level semantics like parallelism have to be stored behind separate runtime calls, or even in the case of a GPU kernel, in completely separate modules where they can't interact with each other. And even worse, any other high-level semantic properties, especially on algorithms or data structures, can't be concisely represented and thus are lost. So as an example, let's look at this little code snippet on the left that takes some arbitrary data structure, and I first get the size of that data structure. I then insert an element into it, and then finally I print the size of it again. Now, when I go and compile this, I get the code here on the right. First, I see the call to size, then I print it, I then insert that single element into it, and then I have to call the size function again. And the reason for this is even though I know from the semantics of that insert instruction that the next size will just be 1 greater than the previous size, the LLVM representation has no way of knowing that. So it has to now call size again instead of being able to have this nice high-level optimization, understanding that the size is now just incremented by 1. So here's where MLIR enters into the picture. So MLIR is a new compiler infrastructure explicitly designed for both reuse and extensibility. And rather than, like in the LLVM representation, having a fixed set of individual instructions, MLIR is explicitly designed with the notion of dialects where any individual can add custom operations or custom types. In particular, all of these new operations and types that one adds are designed explicitly to be interoperable and, moreover, can have multiple levels of semantics all in the same time, hence the notion of multi-level IR. And in particular, in addition to a relatively wide set of existing dialects, including structured control flow, GPUs, quantum, circuits, and so on, any individual can directly add a new dialect for whatever their high-level semantics are that they want to go ahead and optimize. And this is exactly what Polygeist aims to do. So Polygeist is a myriad of different things. First of all, it's a generic front-end for C and C++ code that generates that high-level standard MLIR dialect, as well as being able to support generic C and C++ code, compiling it down there. Secondly, from that standard IR, it's also able to raise it to a much higher level representation, such as the affine or sort of polyhedral variant, for use in other high-level analyses. Moreover, it also contains a collection of high-level optimization passes, such as parallel optimizations, a more generalized mem-to-reg, and a couple of more, which enables it to run even more high-level transformations, such as that polyhedral optimizations by integrating in now the polyhedral optimizer or scheduler known as Pluto, as well as novel parallel and GPU-specific optimizations and transformations. So let's see how this works in practice. So I've got that same code set here on the left, and I have on the right the sort of direct lowering that we'd see right out of the Polygeist frontend. Now, this is before any of these optimizations occur, and as you can see, it's a little bit verbose, but I've gone ahead and highlighted the relatively important parts. So in particular, we can see that we have here the SCF4 as representing directly that for loop in the source code. We have the ability to represent sort of generalized variables as arguments. So whereas we might have had originally this pointer to an integer, we could have, of course, overwritten that pointer to an integer, so we have to store it in a generalized variable. The other thing that you'll note here is we don't have a pointer type used directly, but we have something known as a memref type, or memory reference in MLIR parlance. And specifically, that's used to represent the fact that not only do we want to have the fact that this is a pointer, but we also want to keep any structure information. So as an example, if right here I had the fact that I knew this was an array of 20, 10, whatever, then that's going to be explicitly included in that high-level type, which also makes doing some of these analyses a little bit easier. So now let's actually go ahead and see how this transformation works within the optimization framework. So again, we have that first little bit of MLIR code that's directly output by Polygeist Frontend. We first go ahead and run that mem2reg pass so we can get rid of those unnecessary allocations, unnecessary stores, and we've now got it with a little bit of excess here, but still relatively nice. The next notion here is we run a pass known as canonicalization, and this pass effectively says that we can define for any individual operation a set of rewrite rules that will go ahead and simplify it. So as an example, if we had a constant plus another constant, we can easily replace that with a new constant, but moreover, if you had your own custom operation, you could define your own custom canonicalizations that would all intermix with each other at this level. Next, we have the notion of raising to affine. So whereas before, we see this SCF4, which is just some generalized structured control flow 4, which in this case goes from 0 to 10. Now we have this raised to an affine 4, which represents the fact that this is pseudo-polyhedral. And if we look at the store here at the bottom, we have this indexed at 2 times the individual index argument. Now, if we actually go ahead and we look at the difference between that left-hand side, that code that's emitted after all this high-level raising procedure, and the right-hand side code, they actually look fairly similar, and that's due to the fact that we're able to both preserve that high-level information as well as raise and detect any of the high-level information within it. So I'm going to begin by talking about 2 specific case studies that we've done using this ability to represent the high-level semantics of the code. In particular, the first case study is going to be one of polyhedral optimization, and this was first published in PACT last year. And then the second of which is being able to take generic GPU code, understand the parallelism within that GPU code, and moreover, transform it and get it to run in a completely different system than it was originally targeted for. So let's start by talking about the polyhedral model. So the polyhedral model is really nice in the fact that it's able to do lots of high-level transformations and optimizations that are otherwise difficult or cumbersome to express on a lower-level IR. So in particular, if you have, say, a multi-dimensional loop nest, it represents all the work that you would do inside of that multi-dimensional loop nest as being indexed inside of a generalized polyhedron. So if we have 2 loops that iterate through I and j, we have this little thing here on the bottom left, and we can represent the work as points in a multi-dimensional space. And the different types of transformations that we'd want to use, such as loop interchange or tiling or the likes, can be represented as just transformations on the iteration space itself. This actually turns out to be really, really useful for a bunch of different domains, in particular within machine learning frameworks as well as generalized scientific computing. The polyhedral model has been found to be one of the best ways to exploit the different types of parallelism, locality, both in terms of space and time. So polyhedral compilation is currently done in 2 different forms today. The first of which is, if we look back at that same compilation pipeline that we saw earlier, either we could apply directly on the C and C++ source code side, and there are 2 different tools that are used for this, such as Pluto or PPCG. And this has the advantage that because we're taking the source code directly, we already have that direct high-level syntax as written. However, in contrast, as we saw earlier, the polyhedral form is relatively unhappy if it isn't perfectly within that representation. So it may need some additional optimizations, such as alias analysis or otherwise inlining certain code to be able to deduce the bounds of loops. And because these tools have to operate on the source code directly, they can't run any of these optimizations beforehand. So they're stuck with, if you wrote it exactly perfectly inside of that model, you may be able to go ahead and run it, but if you're just a little bit off of it, or otherwise you need some optimizations to get you there, you're going to be a little bit stuck. The second way of doing this is to, instead of try to take all that high-level information and hope that it is in the correct form to begin with, to try to go from the low-level information now, after optimization, and raise it up and find all those polyhedral parts of the program. So examples of this, say, in the LLVM framework include Poly. If you like GCC, there's another tool called Graphite. And this sort of fixes a little bit of that earlier problem, since now we can run optimizations first. But it also comes with the caveat that finding all of those polyhedral parts of the program from the low-level side is a difficult problem. You have to sort of pattern match to some extent, as well as the fact that some of the optimizations you might have done, like loop invariant code motion, actually can get in the way, and you have to kind of undo them to go and find those relevant polyhedral portions. So rather than relying on either the source code level, where all that high-level sort of semantics is there, or the low level, after which optimization is applied, Polygeist explicitly aims to get the best of both worlds by directly preserving those high-level semantics inside of the optimizable IR. So specifically, we're able to preserve those high-level polyhedral/affine semantics, as we saw earlier, and do a lot of these new optimizations. In particular, we're able to do optimizations that are very difficult to do on either the source code level or the low level, because implementing them requires combining these two pieces. As an example of this, we have the notion of what's called statement splitting. So if you have a very large line where you have a store to some memory operation with a complicated sets of loads where you multiply and other pieces together, rather than considering that to be an entire statement inside of that iteration space, we can actually break them up into smaller sub-pieces, which actually allows us to get a little bit better. Moreover, we can detect parallel reduction, since directly inside of this representation, we have the notion of parallelism, so we can directly deduce and find any of these sorts of pieces. So specifically, if we look at sort of the impact of this in contrast to some of these other tools, we have the same sort of set as we saw previously, except now we have this mul function in between. And because that mul function isn't directly inlined, a tool such as one that applies on the low level, like Pluto, can't actually, or sorry, like Poly, can't figure out what the index behavior is of that store, and thus has to give up, whereas now, of course, we can just inline it and figure it out. On serial programs in particular, comparing against the LLVM or compiler-based tool Poly, we get an 80% speed up. Comparing against on serial code and on the high-level C and C++ IR, we're able to get an 8% speed up. Now, on the parallel programs, where we're also able to take the serial source code in and automatically deduce what parts are parallel, we get an 190% speed up over the IR level tools and a 26% speed up over the source-based tools. The second case study that I'm going to talk to you guys about is that of GPU compilation. So suppose we have this little code here on the top right. So specifically, we have this normalized kernel, and we also have the corresponding launch code. So the normalized kernel runs on the GPU. It takes in two arrays and sets the output array to be the input divided by the sum of all of the inputs. And that has to run, in particular, on the GPU, because we want to take advantage of all of the available threads. However, the code that actually goes and calls it is host code. It runs on the CPU, and when you try to compile this with LLVM, you actually find that there's two distinct modules that are created. We have one for the host code, which has these sort of CUDA launch configurations, any high-level context or copies that are necessary to be able to set all this infrastructure up, as well as the device code that just sees the individual kernel that's being called. Moreover, also, even if you look at the device code, it's unclear that this is being called multiple times, though if you know that this is a GPU kernel, you can potentially guess, but still, there's no even notion of a loop here, since in theory, we're calling this inside of a parallel for loop. And this relative lack of a nice representation from parallelism hinders greatly the ability to do optimizations, because first of all, these two individual pieces of code being in separate modules means that there's no way to communicate either the outside structure of how this is being called in, or the ability to move code from the device outside, or other simplified, because we know all this higher level context. So here we aim to explicitly preserve that parallel structure. Because we're in the MLIR Compilation Framework, we're able to now use these high-level operations, such as a generic parallel operation, to not just have that host code and device code, but have them all in the same place. And not only are they now in the same module, but in fact, this actually looks like a reasonable parallel for loop. They're even in the same function, and this allows us to potentially move code around this context, better optimize the context, and just generally understand exactly what's going on. So in this case, suppose that I'm going to now retarget this code from GPU code to CPU code, since it's just a generic parallel, and I notice that this sum call is being called every iteration of the parallel for loop. I can actually hoist this outside the parallel for loop, potentially saving us, potentially O of n squared work, reducing it down to O of n, which is a very useful thing to do when you're trying to make your parallel code go run fast. The other thing that we're able to do here is, especially in the context of GPU programs, but this also generally applies to other sorts of parallel programs, it's important to have the notion of some sort of synchronization. So on this code here on the right, we see code A, sync threads, code B. And the semantics of this means that all of the threads have to finish executing the call to code A before any individual thread within the block can execute the code inside of code B. Now, currently inside of LLVM type tools, whenever you see one of these synchronization utilities, you immediately sort of have a barrier to any sort of optimizations. You raise your hands, you say, I have no idea what's going on. This code can touch all these other memory, all these other threads, and just stop any optimization from occurring within that section, which, well, technically correct, is not necessarily great for performance. So it actually turns out that we can represent the corresponding semantics here of synchronization through the use of memory. So in particular, if we define the synchronization's memory behavior to be the union of the read and write properties of the code before it, alongside the read and write properties of the code after it, we're able to prevent any illegal optimization from moving code either above down, down up, or otherwise. While simultaneously, if we have any parts of the code that aren't impacted by synchronization, like say an index calculation of fib here, or the likes, it is able to be moved across because that won't affect the memory behavior. Moreover, the fact that, again, we're able to represent this as a union of different memory effects means that other parallel-specific optimizations, such as getting rid of synchronization, moving synchronization, or otherwise doing optimizations on it, are relatively easy to understand and represent, since in the case of, say, getting rid of synchronization, that's equivalent to showing that the memory effects of that individual synchronization instruction is the empty set, meaning that it wouldn't have any actual impact on the code that you're synchronizing. So we can actually now, at a slightly higher level, now the CUDA C and C++ code, see a little bit of how this works in practice. So we have this store here into the node variable from some index input, and we have the synchronized threads that comes right after it. And it turns out that sync threads isn't actually necessary since there's no risk of potentially overwriting node, and there's no load of node before the subsequent sync threads. So thus, that first sync threads is unnecessary. Moreover, and I didn't really go into much details on this for ease earlier, the different forms of shared memory can similarly be represented as stack allicas within a nested parallel for loop. And similarly, alongside the fact that we have a nice notion of the sync threads, we can actually do mem to reg and other optimizations on shared memory. So here we can deduce that we're storing into the same thread every single time, and then we're also loading that same value. So rather than having to do that transfer through shared memory, we can just transform it into a register, get rid of that store, get rid of that load, and otherwise reduce the total computation time, which is pretty useful. Moreover, as I was showing all these examples, inside of the MLIR form, while you can have some GPU-specific dialects and GPU-specific operations, we chose to explicitly represent this with a generic parallel for. And that's because there's nothing GPU-specific about these semantics other than the fact that we have these data constraints, which are well represented by our barrier instruction. And as a consequence, we can actually go ahead and do different sort of transformations that enable you to run this on a non-GPU specific architecture, like a CPU. Of course, not all architectures have the same notion of sync threads where there's a particular thread group which is going to be optimized on top of. So we need to potentially enable these CPU-style targets that don't have the same group-style synchronization to be able to execute a group-style sync. One particular way that we're able to do this is a technique known as loop fission. So we have the parallel for loop here on the left, and then we can actually split around that sync threads with a parallel for loop that just does the code beforehand, and a separate parallel for loop that just does the code afterwards. And then this is equivalent semantics to having that all threads must finish executing code A before any individual thread executes code B. The same form actually generalizes to generic control flow. So for instance, if we had this parallel for with the for loop inside of it, denoting the fact that we could have some iteration over a larger scale space, we can actually interchange the original for loop with the parallel for and then recursively do that splitting. And thus, any arbitrary control flow with fors, ifs, whiles, et cetera, can actually be transformed in this same process. We can now go ahead and actually see how well both those optimizations we talked about for parallel and more specifically GPU codes apply, as well as the ability to do that very high-level transformation to take GPU code and go and execute it on the CPU. So to sort of do this entire grace check, we took both the Rodinia benchmark suite as well as a ResNet 50 training within PyTorch. We took the GPU backend for both of these, because it turns out that Rodinia has GPU codes, as well as, of course, PyTorch has the GPU backend. And we also took the handwritten CPU expert-written version of these. In this case, the Rodinia also has, for many of their benchmarks, both a CPU version and a GPU version, and PyTorch also has two distinct, at least, CPU backends. We compare the runtime of the GPU version, cross-compiled using Polygeist to go run on the CPU against that expert-written existing CPU backend. Now, of course, there's all these crazy things like shared memory and other stuff in the way, and of course the fact that you're writing it for a GPU target means that you're not necessarily optimizing for that same CPU target that those experts were for that original code. So the theoretical best here is sort of, can we get close to matching that expert-written performance? And it actually turns out that we don't just match that performance, but we actually beat those existing CPU backends. In particular, on the Rodinia benchmark suite, we get a 58% geomean speedup over that expert-written CPU backend code. And for PyTorch itself on ResNet 50, we get a 2.7x geomean speedup on training. The other thing that I'll say here is, again, with those two test cases, or two case studies that we talked about earlier, going into both polyhedral and parallel/GPU, those were interesting for our particular needs as first places to explore, but there's no reason why this can't be applied to interesting problems in your domain. And in particular, we actually have a lot of people who we're working with exploring this in a lot of different places. There are folks using this for cycle compilation, which is a little bit close to the GPU stuff, but still interesting. Circuit compilation, BLAS kernels, databases, and more. And if you're interested in applying this to any other sort of places where there's high-level semantics that you want to take into account during optimizations, please try it out, reach out, and happy to talk and work with everyone on it. Now, wrapping back up. So overall, Polygeist is several different things. First of all, Polygeist is a new C and C++ front-end for MLIR, and this is particularly interesting because inside of the MLIR representation, we're able to take advantage of the ability to simultaneously represent a lot of different aspects of the code while simultaneously preserving any high-level semantics that are desirable. Because we have those high-level semantics, we're able to do novel both compiler transformations as well as optimizations just generically on top of this code, alongside that raising that we saw at the very beginning. And in particular, we saw this in the context of two specific case studies, the first of which was polyhedral optimization, the second of which was novel, both parallel and generic GPU optimizations and transformations. And on those two specifically, Polygeist was able to beat those existing polyhedral tools on both sequential and generating that parallel code, as well as Polygeist was able to substantially beat the state-of-the-art for optimizing and even cross-compiling GPU code. We also support the ability to recognize and lower to custom operations or dialects. So again, if you have your own specific, domain-specific information you'd like to take into account, you can do that. And it's an official LLVM incubator project at github.com/LLVM/Polygeist. We have a website, discussions on discourse. And of course, there's a variety of folks and funding agencies that we'd like to thank for their contribution to this work in some way, including both the Department of Energy, as well as several other government agencies. And generally, thank you so much. Any questions?